Hello, everybody. This is a video on the speed of waves through different mediums. First step is to realize that if something is more rigid, it has a faster wave moving through it. So that means stronger connections, which means a higher bulk modulus or a higher tension. Remember, the bulk modulus is a pressure. It's how much a material fights back. When an external force is applied. Right? So you can think of it as the internal pressure or rigidity in a medium. So if something's more rigid, like metal, has high bulk modulus, water and liquids have a lower bulk modulus. And of course, if something is more dense, which means it's heavier, which means the mass goes up, right? Or the volume goes down. Just careful, this is volume now. Then it is a slower velocity. Velocity, volume, careful. Those are not the same V, right? Lower case V is velocity, uppercase V is volume. So this is the concept. And this, of course, comes from that in a 1D wave, say you have like a slinky, if I were to pull this up, it's going to pull this up with some tension, but each molecule has little masses here, right? So the acceleration will be Ft over m. So clearly more tension will make it go faster and more mass will make it go slower. And of course, the opposite, less dense is faster, less rigid is slower, but I'll just write it like this, and the opposite is inferred. Cool. So step one. Step two is the formula. So for a 1D wave, and I'm going to challenge you guys to draw the 3D version this week. But the 1D wave, the velocity that we derived in class is the square root of tension over linear density. You can remember linear density as mass over length because it's one-dimensional. It's the one-dimensional size. So I have a string, slinky, etc. Three-dimensional wave is a solid, liquid, or gas, just any medium like a compression wave. Basically, this is sound. The velocity of a sound wave through metal, through water, through air is the bulk modulus divided by the density. So what these have in common, of course, is this is the connection or the rigidity. The molecular connection is the tension. The molecular connection is the bulk modulus or the rigidity is represented by that. Clearly, if I have a more rigid rubber band or a more rigid slinky, it's going to be more tense. There's going to be more tension. If I have a more rigid metal, those molecules are going to be more connected and therefore more rigid and therefore more responsive. If I hit one end, boom, the other end's going to respond. The next molecule is going to respond more rapidly. Where, of course, this density now, if it's heavier in 3 dimensions, mass per volume in cubic meters, of course. Now we have one-dimensional density matter for one-dimensional waves and three-dimensional density for three-dimensional waves. Cool. This is where we start. This is the math that corresponds with the concept we just said over here. Great. So now what we want to do is go on to gases. And the quick thing is that gases have this formula. The bulk modulus is something called the adiabatic constant, which says that if I squeeze a gas rapidly, like if I do a quick squeeze of, say I have a volume of gas and I squeeze it with some external force, then what happens is the pressure times the volume to this constant is constant. And what ends up happening is that we see the force that fights back the bulk modulus is derived by this formula, which we end up getting, you can show equals the adiabatic constant. Ironically, it's this exponent times the pressure. There's a lot more physics at play here that takes, honestly, weeks to go through. This is thermodynamics. But really, you can kind of just erase it. Don't worry about it. And realize that if I want to squeeze a gas, it fights back with its pressure, right? It fights back with the amount of pressure within it times some constant that's usually like around 1.2, 1.3, 1.4. So adiabatic constant is usually around, right, between 1 and 2. So this is how gases work. So for instance, in air, and this is where what we're doing in class on our worksheet that I'll show you in a moment. But I'll just do the calculation right now. So in air, what we get is the velocity of sound will be the square root of the bulk modulus over the density. So what you do is you just plug in the adiabatic constant of air, which is 7/5 or 1.4. And this has to do with the degrees of freedom of how air vibrates or moves. Again, that takes a minute, but this is just the value for air. Just take it for now. This is just a number that corresponds to air molecules, air being O2 and N2. These are diatomic. Because they're diatomic, they have this value for the adiabatic constant. You don't need to know the physics. It takes a while, but I do want to do these calculations. So I'm just going to give you this number and say, please just plug it in and try to make sense of everything else. So what do I plug in? I plug in 7/5 times the pressure of air. Let's say at atmospheric pressure. At atmospheric pressure, right? What is the speed of sound in air? Well, the atmospheric pressure is 101,325 pascals. I know we said it was 101,000 full stop, but this is actually the more accurate value. 101,325 is more accurate. Divided by 1.225 kilograms per cubic meter, and I get the speed of sound in air. If I calculate this, I think I get 340 meters per second. Now you might have heard, especially you might have heard from me, that it's 343 meters per second. And here's where it gets a little interesting. It's 340 meters per second at this atmospheric pressure and this density. Oh, sorry, I have an extra 2 there. So let's take a look at this a little more detailed, right? Watch this. This is kind of cool. This is where this formula comes from that I want you guys to know and be able to use. The bulk modulus for a gas is the adiabatic constant times its pressure. But you might know that there's something called the ideal gas law, PV equals nRT. R is the gas constant, 8.31 joules per mole degree, what's called Kelvin. T is measured in something called Kelvin. Kelvin as a temperature is Celsius plus 273.15. So 0 degrees Celsius equals 273.15 Kelvin. 20 degrees Celsius equals 293.15 Kelvin, etc. This is like room temperature. This, of course, is freezing water. So that's pretty easy. So what I can do is solve for the speed of sound as the square root of bulk modulus, plug that in there, adiabatic constant times pressure over the density of some gas. But the density is mass per volume. So what I get is the velocity of sound, and maybe make sure that this is a lowercase v. Oh yeah, this is volume here. This is velocity here. Velocity of sound is the square root of gamma times p over m times v. And this is volume here, right? Which is, if I flip and multiply, gamma times pv over mass. And so PV equals nRT, I can plug in here and I get that the velocity of sound in a gas is the square root of gamma times nRT over the mass of the gas. But the mass of the gas, right? And this is like the important last step, is what's called the molecular mass, which is kilograms per mole, times the number of moles. Kilograms equals kilograms per mole times the number of moles. So I can just plug that in there. This is called the molecular mass, which is the atomic weight, which you might have heard, or the atomic mass, I think is actually a better word, the atomic mass, right? Atomic or molecular mass on the periodic table, right? So for instance, carbon has 16 grams per mole. So we would want 0.016 kilograms per mole to plug in there if we were just doing pure carbon, which isn't a gas. So we have to be careful what we plug in here, and we need to add up all of the molecular masses to do this. But we're one step away. The velocity of sound in a gas is the square root of gamma times nRT over the molecular mass times n, because I just plugged this in here, and the n cancels, and I get the velocity of sound in a gas is this formula, or a gas only. So what does this tell us? This is really important. The velocity of sound, v of sound, depends on what? Temperature and molecular mass. It depends on temperature and it depends on mass, which means that temperature is now the connection, because temperature determines pressure, right? So if you have a higher temperature room, the molecules have more pressure, so they respond faster. They have a higher bulk modulus. Technically, hotter air is more rigid, which makes sense. It's trying to push outward, right? So it resists compression. It has more pressure in it. Clearly, if it's heavier, if you have carbon dioxide versus helium, carbon dioxide is heavier, or even oxygen, O2 is heavier. So it's going to move slower, right? So we can use this to solve for the speed of the temperature at which we were calculating the previous example. We got 340 meters per second. Now what we can do is we can write down V of sound in a gas equals the square root of gamma RT over M, where M is the molecular mass. For air, the molecular mass is a combination of O2 and N2 at very specific percentages. It's like 70% O2, sorry, 70% N2, 28% O2, and you get an average of 0.0287 kilograms per mole, which is 28.7 grams per mole. You can do that calculation yourself, but I'll just give that to you. R is 8.31 in our units that we need, Kelvin and joules, and I want to solve for T. if V is 340 meters per second, because wait a minute, I thought it was 343 meters per second, right? Solve for temperature if that's that. So 340 equals the square root of, and then of course, gamma for air is 1.4. Square root of 1.4 times 8.31 times T over 0.0287. And what I get, I'm going to do it right here just to make sure I'm doing it right. What I get is 340 squared times 0.0287 divided by 1.4 divided by 8.31. I get temperature, sorry, this is an 8. This is just plugging in this number here. 0.028, so 0.0287. So I get T equals 285.17 Kelvin. And if I subtract 273.15, I get that this is 12 degrees Celsius, which is the average temperature of atmosphere on the Earth, which is why this is corresponding to atmospheric pressure and corresponds to the density of air being 1.225. Isn't that interesting? So if the temperature goes up, air expands, it becomes less dense. It also becomes more pressurized, which means sound goes faster. Let's review what I just said. If the temperature goes up, what does that do? It makes density go down because it expands, and it makes the pressure go up. So if V is the square root of bulk modulus over density, density went down, bulk modulus went up. Both of these individually, this makes V faster, and this makes V faster. So this is why temperature increasing makes it go faster. There's more pressure and it's less dense. So both of those correspond to an increase in velocity. So what about 20 degrees Celsius? Well, that's going to be Kelvin equals 20 plus 273.15. So Kelvin is 293.15 Kelvin. The temperature is 293.15 Kelvin. So let's plug that into the speed of sound. Speed of sound is the square root of 1.4 times 8.31. What I love about this formula is that you don't need to calculate the pressure or the density. We derived it using that. So it only depends on the temperature and the molecular mass, because ultimately that's what it comes down to. This reveals that for a gas, the temperature is what matters. That's the connection between molecules, is how fast they're vibrating into each other. 0.0287, and we get 1.4 times 8.31. Try it yourself if you're doing this at home. Divided by 0.0287. Join me, please. And to the 0.5. So I get 344 meters per second. That's what I got. 344.72 meters per second, something like that. So now we're around the 343 mark. So around 20 degrees, we get around the 343. And so where the 343 comes from is like this average room temperature, this more like comfortable temperature. But really, you're going to notice the speed of sound in air is quite variable. It's 340 meters per second at 12 degrees Celsius. It's 344 degrees at 20 degrees Celsius, right? So it's really changing depending on what the temperature is. It's like this very it's very variable, right? And so we can go from here. Actually, one more thing I do want to do, might as well while I'm here, is if we look at, where are we here? Well, that's pretty cool. I'm just going to do this though, because while I'm at it, if V equals the square root of gamma RT over M, then we can compare V1 and V2, like the ratio of V1 and V2 for the same gas, so for air at temperature T1 and T2, then it's going to be the ratio of the square roots. So say T1 is 293 Kelvin and T2 is 273 Kelvin. Then the velocity 1 over the velocity of 2 will equal the square root of 293 over 273, which is going to equal, let's do that math real quick. 293 divided by 273. Don't forget to square root it. Equals 1.036, which just means that the velocity is going to be 1.036 times the velocity at temperature 2. So the velocity here is a little bit bigger than the velocity here. So using ratios as a shortcut, and notice if you multiply that times 340, sorry, not multiply by 340, but this was at freezing, not at 12 degrees, right? If you, what was this, 344 meters per second, right? The velocity at that temperature at 20 degrees. If you divide 344 divided by 1.036, you're going to get that the temperature V2 is going to be 332 meters per second at 0 degrees Celsius. So you can use ratios to figure out this difference between the speeds at two different places, or sorry, at two different temperatures. Cool. I hope that made sense. The ratios is a cool thing. All you have to do is isolate the variable in the formula and treat everything else as constant, and then just see how the formula tells you um, uh, just in ratio form. I realize I didn't explain that well. Let me actually go through that right now. I kind of want to go through that because I want that to make sense. Ready? So if you have V1 over V2, that's going to equal gamma R T1 over M divided by gamma R T2 over M. And notice how everything cancels but the T's because they're constant, right? Cancel, 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 cancel. So for ratios, constants, constant variables, they don't have to be constant. They could be variables that are not changing, or anything that's not changing turn into one, right? And then you isolate what changes. And then you plug in the change, then you plug in the proportion. So here we just say V is proportional to the square root of T, or V1 over V2 equals the square root of T1 over T2. Now, if M was also changing, we would get that V goes as square root of T over M, if M is not constant, right? Obviously, adiabatic constant and R should be constant, right? But if we're changing the actual mass as well, this is the proportion equation. We can plug in the proportion change. So maybe the mass doubles and the temperature quadruples. And then we get V goes as the square root of 2, which just means it's square root of 2 bigger. Because I plug in 4 times bigger on top, 2 times bigger on bottom, and I get it multiplies by root 2. I think if we do problems like this, it's going to make sense. I kind of don't want to go in more detail now, but I hope that made sense. If it didn't, don't worry about it for now. If it did, you're good. I think it's a good time to pause. See you guys in class.